We from the team of Step Up Bengal welcome all the CSIR net or WB set aspirants in the next lecture of classical mechanics. Up to this we have studied Euler-Lagrange equation, or sometimes it is called simply Lagrange equation, which is given in this particular question. Now we will go deeper into Lagrange equation and try to solve a question of 3 marks, that means single choice, in CSIR Net Math June 2016 question paper. First of all, we are now very much familiar with this equation. This is Lagrange equation, where L is obviously T minus V. This T was kinetic energy, this V was potential energy, as we have already discussed. If you are not familiar with these two, then please visit lecture 8 and 9 to have clear idea about kinetic energy and potential energy. So without any further delay, let us start the problem. This particular problem is actually again a mixture of two ideas. We can call it a mixture of two important ideas. What are those two ideas? We will first see in brief. আমরা শুরুতে এটাকে briefly দেখব, and then we will discuss the problem, or rather the solution of the problem. Since it is a 3-mark question, so only one option is correct. But which one? Let us see. First idea, that is very peculiar idea. If we just consider spring mass system, to have the idea clearly, we just take an example. Spring mass system. As all CSIR net or WB set aspirants are very much familiar with a particular terminology that is called counter example, because in real analysis, in linear algebra, often we use counter examples to tackle the single choice question to eliminate options so that the correct option automatically stands out. In dynamics also, or rather in classical mechanics also, we should and must use counter example. This is very important to handle the problems in a small amount of time in the exam hall. As we have already said several times, that time management is the main factor to qualify this type of exams. Now take a look at the example. Spring mass system. Here Lagrangian was T minus V and T minus V. Here Lagrangian was T minus V. What was T? Half into mx dot square minus what was V? That is half kx square, k equal to spring constant. Now if this is Lagrangian, that means L, take a look at one thing first. Here that V, that means the potential energy, we can call it as a function of only x. That means this is of the type some function of qi, where qi were generalized coordinates. Here we have only one generalized coordinate, that is x, so we have written it as fx. It may be so that this v, that means potential energy, is a function of qi comma t. That means this is critical. Take a look at this very carefully. If t is inserted, that means time is inserted in the expression of potential energy, then if t is inserted in this, then this particular L, which is ultimately written as the difference of t and v, will also contain qi comma t type. That means t will be inserted in L also. And since we all know this Lagrange equation, what was that equation? That means ddt of within bracket del L by del qi minus del L by del qi. Here we should have dot, and that is equal to 0. Now in our case, that means in case of spring mass system, this qi is obviously only one, that is q1, and that is x. So we are familiar to this idea, nothing new in it. What is new, we should mark. Whenever in the expression of v we don't have t, such as in this particular case, or in this particular example, if you see that v is, what is our v? V is half kx square, that is free from time, free from time. Then this particular equation 1, that is the idea. Then for 1, equation 1, t plus v must be constant. This is important result. All of you should make a copy of your own to mark this result. This is extremely critical result for any kind of exam. This v, which is free from time, as in the case of spring mass system, then t plus v is constant. And when this happens, we should have conservative system. Conservative system. That means if any system t plus v equal to constant, we call it conservative system. When it is not constant, that means sum of kinetic energy and potential energy is not constant, then we have non-conservative system. Now take a look at the result again. When potential energy is free from time, we must have only or purely conservative system. We can call it as purely conservative system. That means in that case, potential energy, the sum of potential energy and kinetic energy will be fixed, and that is constant. So we should have conservative system. On the other hand, in this case there is time factor is inserted. Say we have a particular potential energy which is written in the form of x comma t, where obviously x is q1 and t is time. So you can mark this as this particular expression and say this is e to the power xt. So cannot we call it as a function of x and t? That means time is inserted in it. So now the results come: time inserted in potential energy part imply system may be conservative or non-conservative. Now the question comes, what is non-conservative system? In a non-conservative system, t plus v not equal to constant. So if time t is inserted in the potential energy part, again I am mentioning the fact that you should not bother about kinetic energy t. Just take a look at the potential energy part and see whether time is inserted. If time is inserted, it may be conservative, it may be non-conservative. Okay, for purely conservative system, we should not have time in the expression of V. When V is free from time, we have purely conservative system. But when time is inserted, it may be conservative, it may be non-conservative. So this is the main idea. So to have conservative or non-conservative system, just take a look at the portion V and see whether time is inserted or not. If time is inserted, then that is in general conservative or non-conservative, and if time is not inserted, then that is always conservative, as in the case of spring mass system. So in spring mass system, what we have? We have always V equal to half k x square time, that is free from time within bracket t. So this will imply conservative system, and for conservative system, this equation, this Euler-Lagrange equation or Lagrange equation will be applicable to conservative system in that case. But if t is inserted, then it may be conservative or non-conservative. This is idea number one. As I was discussing, two mixture of two important ideas. This is idea number one. Next we go to second important idea, idea two. That is also important. This is called gauge transformation. Actually, this type of transformation is very much important in field theory, famous field theory discovered by Albert Einstein himself, field theory of quantum mechanics. But we don't have quantum mechanics in our syllabus, so we should bother least about that. The thing we all have is only classical mechanics. This gauge transformation is one kind of point transformation. We will just in brief discuss that type of transformation. What is it? It should be point transformation. That means we have seen that L is Lagrangian, which is virtually t minus v. So if we just add one more quantity in L, say this quantity is f, which is a function of coordinate and time, and take total derivative of that kind quantity, we must have a new quantity L dash. This L dash, take a look at the fact that if the quantity added should be and must be a function of coordinate and time. Say this is, it may be e to the power xt, it may be only x square, it may be only x cube, etc. If this quantity is added to Lagrangian, then we have a particular shift in L. This type of shift is called point transformation. মানে আমরা ল্যাগ্রাঞ্জিয়ানটাকে জাস্ট চেঞ্জ করে অন্য একটা নতুন L dash ফর্ম করলাম. Now take a look at the fact that any quantity L that is satisfying this equation must be a Lagrangian. So clearly L, since L is satisfying this equation, so L equivalent to Lagrangian. This is clear as daylight to all of you. But if we add some additional quantity to L and make that as L dash, let us see what happens. Say we have in spring mass system L equal to half m x dot square minus half k x square. So what will be our del L by del x? That should be minus kx. What will be our del L by del x dot? That should be mx dot. So what will be ddt of del L by del x dot minus del L by del x equal to 0 give? What will this quantity give to us? This will give ddt of mx dot, that means mx double dot, minus this quantity, this minus and minus will be plus this kx equal to 0. Is it clear to all of you? This quantity is obviously 0. So this is one thing. Now if we make a new L which is called as L dash, as say this L is already in our hand, half m x dot square minus half k x square, and we add this quantity as in this format. Then what we will have? We have ddt of within bracket x square. So what will be our L? Half into m into x dot square minus half k x square, and obviously this quantity will be plus 2x and x dot, because for x square we have 2x, and then the derivative of x with respect to time will be this. This is our L dash. Now we want to see whether this L dash satisfies Lagrange equation or not. If it satisfies this equation, then L dash will be again a Lagrangian, which is different from L. Now let us see what happens. Just put in the left hand side that quantity L dash. So what is our L dash? L dash equal to half m x dot square minus half k x square, then that additional term, what is that? That is 2x x dot. Now let us form del L dashed by del x. What will be that? That will be minus kx plus 2x dot. Clear? We have taken derivative and partial here and here. This term is free from x, so we should not bother about that. And what to next? Del L dashed by del x dot, and that is equal to mx dot plus 2x, because this term is not containing x dot, so we should bother about only this, and this will give us this particular case. And now let us put these values in the left hand side. So what should we have? But before that, let us make this calculation also. Del L dash by del x dot. This part, what will that part? Who will be that part? mx double dot plus 2x dot. Now let us put in the left hand side, that is here. That means ddt of within bracket del L dash by del x dot minus del L by del qy, that is equal to 0, implies what is this? This quantity has been calculated here. So mx double dot plus 2x dot, and this quantity has also been calculated here. So we should put all these here. This minus kx will be plus kx, and plus 2x dot will be minus 2x dot for this minus sign, and that is equal to 0. This 2x dot will be cancelled, and we have mx dot plus kx equal to 0. This is important. Say it as equation B. Now just compare B with this equation. That means equation, this is our equation number A. Are not they similar? Yes. So it proves the fact that if L is Lagrangian, then L dash formed from that Lagrangian is again a Lagrangian. This is called gauge transformation. This is very important. So what conclusion does this phenomena give to us? That means Lagrange implies Lagrangian is not unique. Though the equation of motion is same, but it is not unique. That means if you have L as half m x dot square minus half k x square, and just we should add, if we add ddt of e to the power xt, is this a function of qi comma t, that means coordinate time function? Yes. Then this L dash will again a Lagrangian. This is the result. This is important result. Several times CSIR has asked question on it. We would see later. Clear? So Lagrangian in general is not unique, but the equation of motion under gauge transformation will remain unchanged. This is important. Under gauge transformation, EOM, that means equation of motion, will remain unchanged. You should mark all these results to solve any problem within say 1 minute. Now we will see that how can we solve. If we have all the ideas, then how can we solve this particular question within 1 minute or so. Now let us read this question. Consider the equation of motion, this quantity, where L is T minus V, and this is important, V as potential energy. Now we are getting within the first bracket T and Qi. That means time has been put in V, or in other words, time has come within the expression of V. So that is why it may be conservative or non-conservative. That is the result we have already discussed. When time is inserted in potential energy part, system may be conservative, non-conservative. Again, Lagrangian is not unique. Now let us see what are given in the option. These Qi are generalized coordinate. These are known to as Qi dot generalized velocities, Qi generalized coordinate, Qi this generalized coordinate, and Qi dot generalized velocity. We have already seen that. Now take these four options and see what is correct. Then এখানে যেটা বলতে চাইছে দেখো, the equation of motion in the form as above are necessarily restricted to conservative system. If we want to restrict this particular equation into conservative system only, then we should not have time inserted in potential energy part, because when this is inserted, that means time is inserted, it may be conservative or non-conservative. So we cannot call it as only conservative system. Here it is written that necessarily restricted to a conservative system, so this is wrong. Next part, not necessarily restricted to conservative system. This is true, yes, but look at the second part. There is unique choice of L, and we have seen by Gauss transformation L is not unique. L is not unique. This result is important. You should mark it with red color possibly in your copy. L is not unique. So obviously not necessarily restricted to a conservative system. This is true, but this is false. So yes plus no ultimately will give us no. So this option is also eliminated. Next, come to the next option. Necessarily restricted to a conservative system. This cannot be true because time is inserted. So this is also gone. So ultimately the answer comes out, and we will see it is a result. Not necessarily restricted to a conservative system by this result, because time is inserted in potential part. So this is not restricted to conservative system, and there is no unique choice of L. It is also true by Gauss transformation. So obviously 4 is correct. So we have seen that if we know all the results, then within 1 minute, 1 to 2 minutes, we cannot call it in 30 seconds, 1 to 2 minutes we can solve this problem. But to solve these problems, we should have all these ideas very clearly. So in this video we should stop here, and if you like this particular segment of classical mechanics, then please comment or share this video lecture so that maximum of students can be benefited free of cost. And our team has recently decided to give a WhatsApp number to all of you also, just to, in case you have any difficulty, just put the message in WhatsApp so that we can satisfy all of your queries up to what we can possibly. It is not always be that we can just help you to sort out all the problems of classical mechanics, but in 90% cases we have to be successful, so that this type of exams will not be a fear anymore to us. So today we finish here. Goodbye, and hope all of you will have a good summer recess.